Hello everybody, we're SimPlane. We're three industrial engineering and operations research students at UC Berkeley. We've been studying discrete event simulation, and this is our presentation about the product that we've created in order to simulate a reconfigurable assembly line. An airplane is composed of a number of base parts. In a traditional assembly line, these base parts enter the assembly line and proceed through a series of workstations sequentially. At each workstation, there's a robot which is specific to the workstation, which performs a number of operations on the base parts. This robot stays at that workstation for the entirety of the process. In a reconfigurable assembly line, these robots are free to move between the workstations. This allows for a more efficient assembly line and allows the manufacturer to have less robots than he does workstations. Let's take a side-by-side look at these two types of assembly. As we've already mentioned, the robots and machines in a reconfigurable assembly line are movable. This allows the actual number of robots in the system to be flexible, whereas in the traditional assembly line, this number is fixed. In a reconfigurable assembly line, robots can serve any workstation, whereas in the traditional, a robot is stuck at one specific workstation. The difference that this makes is that if a robot fails in the traditional assembly line, the entire production process has to stop, whereas in the reconfigurable assembly line, if one robot fails, another robot can move in to take its place, and the production process can continue. Currently, many manufacturing facilities are still using the traditional system. Many of them are hesitant to switch to a reconfigurable assembly line as they fear they will waste time and money trying to determine an optimal strategy in the transition process. With that being said, our goal as a company is to provide you with the most helpful and user-friendly product for determining an optimal strategy to facilitate your company's transition to a reconfigurable assembly line. This is a very simplified version of the model we've used to simulate this manufacturing process. If you look, the model is built of three main parts. In the top left, the user is able to input all of the data that is specific to his or her manufacturing facility. This includes data such as the number of workstations in his system, the number of airplanes he produces, and specific instructions about how to build each type of airplane. In the bottom left, we take into account the fact that the manufacturer may produce the base parts for his airplanes in-house. We realize this is not the case for a number of airplane manufacturers, and that's why we provide you with the flexibility to skip over this step entirely if you choose to outsource this process. In the bottom right, this is the part where airplanes are made through the reconfigurable assembly line. They travel through workstations sequentially and come out an entire finished product. Our model shows the flow of a number of entities through the system, both resident and transient. It does this through the estimation of parameters, both random and controllable, that are users defined. The performance measures used in our model are efficiency, service level, and productivity. Efficiency is measured by the utilization rate of robots and machines. Service level is measured by the amount of time it takes to produce airplanes, and productivity is measured by the amount of airplanes you can produce yearly.
So now, why you should choose our product? There are at least 4 benefits you can get by using our product. This is what we proudly call as the SimPlane advantage. First, customizable user inputs. Next, rich features. Next, various statistical data. And last, user-friendly interface. Customizable user input. As I have previously mentioned, our product gives you the freedom to model your system by considering both random input parameters and controllable design factors. Random inputs, for example, order arrival rate, job processing time, rework probability, and many more. While controllable design factors such as base part requirement, job specifications, number of machines, and so forth. So again, the flexibility is yours. Rich features. Since we are simulating a reconfigurable assembly line, of course the first feature is its ability to simulate assembly line processing. Secondly, our product also considers simultaneous parallel manufacturing, which perform multiple jobs at the same time. Then it also helps you to simulate if you have specific path for each particular job in the system, movable robots, and hierarchical workstation. Furthermore, our product simulates tandem queue with buffer, block and unblock scenario, and rework process. And last but not least, our product also keeps track the status of both resident and transient entities. Next advantage is various statistical data. Using these various statistical data, you can get information that will help you to determine what is the best policy to use in your system. Some of the examples are total manufacturing time, machine and robot utilization rates, length of queue, and many more. Here are some of the screenshots of the graphs that you will get. The first two graphs at the top are the average queue length of each machine and each workstation. Then, as you can see, on the bottom left is the lead time graph, and on the bottom right is the robot utilization graph. So now let me allow Arthur to explain more about the next SimPlane advantage, user-friendly interface.
So, as part of the SimPlane advantage, we offer to you a user-friendly interface that's simple, attractive, easy to navigate, and requires no training at all. Let's jump right into the product, shall we? Here we have the SimPlane simulator, which takes a number of inputs, as Edric mentioned earlier, and provides the user with a number of outputs. At the control panel below, the user can modify experiments, change settings, view results of the simulation run, and of course, enter the simulation page itself. Here we have the experiments page. The user can input the names of output files, append a flag, Y, to append the output to the run. You can also specify a random seed number to start each simulation run and trace the events. Next, you enter the mean and standard deviations in days, or whatever time you may prefer, of arrival times for each type of plane, as well as the number of each type of machine in the base part production system. And finally, the user can specify the number of robots to do the final assembly. On the Manage Experiments page, the user will use this form to enter all the experimental data, as shown on the previous slide. After you enter your experiments, you'll want to enter the specifications for each type of plane. Here, the user can specify the number of required base parts for each type of plane, the number of main body sections, the number of wings, and the number of engines. Next, of course, you will need to input data for the job paths of base parts in the base part production system for each base part of each plane type. And on the right, you will enter the processing times corresponding to each job you entered on the left. Now for workstation specifications. Here the user will enter the number of different types of workstations and the lower and upper bounds of processing times. Also, enter the number of buffer spots in the buffer field for each workstation. You can also enter the probability of a plane needing to be reworked, consistent to the user's own assembly system. Now, after inputting all this information into our simulation tool, we get some results. Here, we have a graph of the total number of airplanes produced in 1 year. As you can see, we have produced approximately 100 airplanes in 365 days. Our next output graph shows the total time each plane spends in production. Here, over a time period of 1 year, each plane spends an average of 10 days in production, as you can see here. And now, Sean will discuss the current market for our product.
Let's take a look at some of the factors that make this market potentially very profitable in the coming years. As you can see from this graph, with the exception of just after September 11th, airline traffic has been increasing at a fairly steady rate of about 5.3% in the past 20 years. In addition to that, the number of aircrafts worldwide is expected to nearly double in the next 20 years. Most airplane giants, including Aerospace and Boeing, are already using sophisticated simulation products in order to optimize their manufacturing process. We don't want you to get left behind. With this in mind, the choice is simple: SimPlane. Please take note of our contact information and feel free to contact us if you have any questions about our product or pricing. Thank you very much for listening.